let me go back to controlling a robot. Controlling a robot involves directing its components through programming or manual switches, similar to managing voltage levels in a circuit. In robotics, you use programming to define actions and responses, translating higher-level commands into specific states, such as activating motors or changing direction. These specific states correspond to voltage changes. We were discussing mobile robots for digital farming, like an automatic robot that you can set on a field and let it go. While it's expensive, you can do less work by controlling it remotely, much like a toy car from childhood. You can create software that directs the robot based on your inputs, making it more hands-on than simply purchasing a ready-made solution. Binary states are key here. Just as computers process binary data, ones and zeros, robots operate on active high-voltage signals and low inactive voltage signals, which dictate their actions. Pulse width modulation, PWM, controls the pulsing of these signals, creating a pulse that manages how power is directed toward different mechanisms. PWM generates a series of on-off pulses, where the on state represents high voltage and the off state represents low voltage. The duty cycle, which we talked about earlier, is the percentage of time the signal is in the on state during one complete cycle. A higher duty cycle means more time in the active state, leading to more power delivered to the load. For example, a 50% duty cycle means the device receives power half the time, effectively averaging the power level. In robotics, PWM can control servos and motors, directing their speed and position by varying the pulse width. This precise control enables smooth and responsive movement. When building a robot, we must consider how much power to direct toward each mechanism. This requires mathematical and geometric thinking. High-dimensional geometry, including concepts like geodesics, parallels horizontal and vertical partitioning in computing. We utilize SMPS, switching mode power supplies, and PWM to manage energy flow through the mechanisms we create, which become the components of the entire system. Within the mathematical and geometric foundations of robotics, we have power management that employs mathematical modeling using tools like Fusion 360 or MATLAB. This involves geometric considerations, control systems, and partitioning. Integrating mathematics and geometry enhances efficiency, predictive analysis, control, and optimization, essential for working with renewable energy. Mathematical modeling helps us calculate power requirements and understand the relationship between voltage, current, and resistance, which is described by Ohm's law. This understanding guides how much power to direct to each mechanism based on its load characteristics. I've been discussing this for over an hour, and my brain is getting a bit tired. This emphasizes the importance of broad knowledge. We've made many connections without diving too deep into each topic. Even if you're not an expert in programming yet, having this understanding will guide your programming efforts. It's essential to know your goals so that your expertise aligns with them. Programming is about expressing ideas effectively. It's crucial to evaluate your learning goals regularly, what you need to know, and how it fits into your broader understanding. A multidisciplinary approach is beneficial, allowing you to connect various disciplines without getting lost in the details. Okay, so we start with efficiency calculations. We're still in mathematical modeling, using formulas to analyze losses in power supplies, like switching power supplies, SMPS. This enables us to design more efficient systems by optimizing duty cycles and minimizing waste. Next, we consider geometric considerations. When we look at the term geometric, we see it consists of geo and metric. This essentially tells us about the path of a line, as one of the foundational axioms of geometry is the concept of the infinite line. Geo refers to geography in a 3D space, while metric relates to the distance that the line spans. So, geo, meaning Earth, captures the spatial aspect, how objects relate to each other in a given space, whether 2D or 3D. In robotics, this relates to the physical arrangement and movement of parts concerning the environment. Now, let's move on to kinematics and motion planning. Robotics relies on geometric principles to calculate paths, angles, and positions. Understanding the robot's workspace involves geometric transformations and spatial reasoning. We ask simple, fundamental questions like, where is the energy going inside this mechanism? How is it flowing? Why do we need it here? These straightforward questions lead us to deeper understandings. If you can't explain something to yourself as if you're 5, you probably don't fully understand it. Now we come to geodesics in high-dimensional spaces. We use this concept to understand abstractions like voltage and programming, helping us map how all parts of the robot or mechanisms work together within a space. This is where modeling, both mathematical and geometrical via CAD software and simulation software, comes in handy. In high-dimensional spaces, geodesics represent the shortest path between points, similar to optimizing energy flow in a robotic system. This concept can inform efficient movement strategies and energy usage. Next is data partitioning, which can be horizontal or vertical. These concepts can be applied to organizing data in robotics. For instance, you might partition tasks or sensor data to optimize processing and decision-making. Mathematically, this involves analyzing relationships between different components and their energy consumption. When you analyze relationships geometrically, it aligns with the concept of geodesics, looking at connections between different points or components and their energy consumption. Now, let's talk about control systems and feedback loops. Feedback loops are essential and very efficient in nature. For example, closed feedback loops exist in salinity gradients and the electromagnetic gradients in cells. The cells in your body have negative and positive feedback loops that rely on membrane permeability and the movement of salt and potassium in the circulatory system. Mathematical models help design control algorithms that adjust PWM signals based on real-time sensor feedback. While applying these concepts in real life can be challenging, we're laying the foundations of robotics, optimizing the robot's performance. Think of the human body, where senses provide information for cells to act. Feedback loops and mechanisms rely on electromagnetic gradients to help understand these interactions. We also have stability analysis, which involves calculations using calculus and differential equations. Studying these subjects can significantly enhance your understanding of systems. By analyzing system stability, we ensure that our robot responds predictably to control signals, much like the brain does. In summary, by modeling systems mathematically, we can identify the most efficient pathways for energy flow and movement, minimizing power loss and optimizing performance. Mathematical models allow for simulations of various scenarios, helping us predict how changes in one part of the system affect the whole. Let's go back to predictive analysis. Predictive analysis allows for simulations of various scenarios, helping predict how changes in one part of the system affect the whole system. This is why programming with a geometrical mindset is important when creating a program for your robot. You should document it in a way that is geometrically sound, which also means mathematically sound. This involves spatial mapping, path planning, and kinematics, all of which contribute to clarity in design. Key aspects include predictive modeling, optimization, error reduction, documentation, and maintenance. To achieve this, we use geometric data structures that represent spatial relationships. Familiarity with data and software engineering concepts is essential for making effective robots affordably. These data structures represent spatial relationships in the form of vectors and matrices, facilitating calculations and transformations. We also implement mathematical functions for common geometric operations like distance calculations and angle measurements to maintain consistency and accuracy. Creating visual representations is crucial for effective programming, as it helps illustrate the geometry involved in the robot's movements or workspace. Understanding this geometry is important, especially from perspectives like physics and electromagnetism, particularly when working with renewable energy and converting AC to DC. We must comprehend how energy flows through these mathematical models, matrices, vectors, and angles in the robot's design. It's essential to understand how energy behaves within the geometric framework, as energy is inherently kinetic and moves at an atomic level. We'll revisit this topic in the next discussion, as I've been at it for quite a while now. As I was saying, you can use SolidWorks to map all this out. The only problem with SolidWorks is the price. The standard license costs about $4,000 to $8,000, but educational and student versions can be lower. Are there any alternatives to SolidWorks that not only have 3D modeling but also simulations? You have alternatives like Fusion 360, PTC Creo, ANSYS SpaceClaim, and Siemens NX. Fusion 360 is around $500 a year. PTC Creo costs about $2,000 for a basic license, while ANSYS Space Claim is around $4,000 for a license. CAD software can range from $10,000 to $20,000, similar to Siemens NX. So, Fusion 360 is probably the best option. Can Fusion 360 simulate electromagnetic induction using a coil and a moving magnet with ferrofluid? It does have simulation capabilities, but it may not specifically support detailed electromagnetic induction simulations involving those components. There's software specifically designed for that, such as MATLAB, which can model complex systems, including electromagnetic systems with custom coding if you know how to code. MATLAB is around $2,000 for an individual license. What about COMSOL Multiphysics? You're looking for cost-effective options, and if you can program, both Fusion 360 and MATLAB are strong candidates. MATLAB can handle complex mathematical modeling, and AI tools like ChatGPT can assist with math as well. ChatGPT has even passed competitions in terms of its mathematical capabilities. Now, let's download the textbook on the material aspects of ferrofluids. I'm going to save it on my phone and then open it in Google Drive on my computer. In robotics, we're using DC, but a lot of the renewable energy systems we discuss produce AC. Therefore, we need to consider DC to AC conversions. Robotic systems currently use DC motors, which are easily controlled for precise movements. To integrate with renewable energy, we'll need an inverter or converter to change AC to DC. What inverters and converters can we use? We can convert AC to DC using rectifiers, which come in two types: half-wave and full-wave. Half-wave uses a single diode for low-power applications, while full-wave employs multiple diodes, like a bridge rectifier, for better efficiency. There are also switching power supplies, which are more efficient than linear power supplies. They can convert AC to DC while regulating output voltage. Linear power supplies are simpler but less efficient, utilizing transformers and linear regulators to produce stable DC outputs. In the context of energy utilization, we want high-efficiency rectifiers, such as Schottky diodes, which have lower forward voltage drops to improve efficiency in rectification processes. We can also use bridge rectifiers for full-wave rectification. Switching power supplies include buck converters that efficiently step down voltage, ideal for charging batteries from renewable sources. When discussing voltages and energy manipulation, programming plays a significant role. Programming allows us to control energy flow, translating binary instructions into actions. In binary, 1 represents high voltage and 0 represents low or no voltage, which forms the basis of digital logic and operations. This parallel between electrical concepts and computing can enhance our understanding. For example, in a switching power supply, rapid switching occurs between active high-voltage states and low-voltage states, similar to binary representation in computing. SMPS, switched-mode power supplies, use transistors that turn on and off rapidly, creating a pulse signal that alternates between active and inactive states. Lastly, pulse width modulation, PWM, controls the amount of power delivered to a load. This format breaks the content into manageable and focused points, perfect for presenting complex ideas in a clear and structured way. All right. I'm on page 147 of our numbers reel by Brian Clegg. This is Maxwell's Mathematical Hammer chapter. Whoever had the book before me was nasty. Okay, let's just say that. Anyway, I wanted to talk about something from this book regarding farm tech, because Maxwell worked on a whole range of things. Notably, he focused on the use of statistics, thermodynamics, and the use of polarized light to monitor strain in transparent materials. His real legacy was his work on electromagnetism. We were talking about salinity gradient power, copper electrodes, PCMS, thermochemical energy storage, ferrofluids, magnetochemical looping, biomass renewable energy, electromagnetic gradients, and the idea that no kinetic energy is wasted. We're going to focus on Maxwell, James Clerk Maxwell, and his predecessors like Michael Faraday. Faraday had a revolutionary way of considering phenomena by imagining that electrical charges and magnets produce a field. His concept was like a contour map filling all space, where the values reflected the strength of electromagnetic phenomena. For example, When a wire cuts through the lines of a magnetic field, it produces an electrical current. Now, if we had hilly terrains like we discussed previously in contour farming, how water flows down hills and creates a buildup of minerals like lime, and we relate that to the concept of a contour map and electrical charges that produce a field, imagine using copper and magnets with the natural contour of the hills. What kinds of mechanisms or systems exist that combine these ideas into something engineered? If we laid copper along contours, we could create a system utilizing electromagnetic induction. For example, if a magnet moved relative to the wire, it would generate an electrical current. This could be harnessed for renewable energy systems in hilly terrains. Solar panels, installed along the contours of landscapes, could maximize sun exposure and use water for cooling. Copper wiring could be integrated into energy storage systems, creating localized energy generation. In contour farming, water runoff can carry minerals, and copper piping in aquaponic systems could regulate nutrients and promote plant growth while affecting electromagnetic properties in the soil. Copper grounding systems can protect electrical equipment from lightning strikes, and natural mineral buildup in the soil could enhance conductivity, benefiting both agriculture and electromagnetic applications. By applying electrical currents through the soil, slopes could be stabilized, water flow altered, and mineral deposition controlled. Integrating electrical systems, especially with copper wiring and magnetic fields in agricultural settings, poses some risks. Fire and shock hazards are a concern if these systems aren't managed properly. Overloads, short circuits, and electrical shocks could occur, especially in moist environments. Proper insulation, grounding, and routine maintenance are critical to preventing hazards. We're just exploring these ideas to understand how they work. Electromagnetic phenomena are fascinating. Although Faraday was a visionary, he had little mathematical training. Maxwell, on the other hand, was the first to apply mathematics to Faraday's field concept, transforming our understanding of electricity and magnetism. To model a field mathematically, you must account for how it extends infinitely through three-dimensional space. Maxwell extended calculus to cover this, dealing with forces produced by magnets and electrical charges. When we think of voltages in electricity, we use tools like PWM, pulse width modulation, and SMPS, switched mode power supply, to control voltage states in devices. Voltages in digital systems represent binary states, ones and zeros, high voltage or no voltage, but there are nuances. Analog signals can take on a continuum of values, not just high or low. These voltages are influenced by electromagnetic fields, which can vary continuously in space and time. In terms of fields, each point in space is described by the strength and direction of electric and magnetic fields created by charges and currents. Differential calculus is crucial for analyzing how these fields change over time. Vector calculus concepts like gradient, divergence, and curl help describe field behavior. In electrical infrastructure, for example, the gradient shows how electrical potential changes in space. The potential difference between a transformer and an outlet is an example of this. The wires carry current away from the transformer, and the gradient determines how energy is distributed throughout the system. Divergence measures how much field lines spread out from a point. Positive divergence indicates a source, like a positive charge, while negative divergence indicates a sink. In the case of power poles, the wires carry current from the power source, like a transformer or power plant. The gradient, divergence, and curl in electrical systems help us understand how energy moves through infrastructure. For example, the gradient shows the potential difference between the transformer and the outlet, and the divergence helps us visualize the spread of electrical current. These concepts are fundamental to understanding how electromagnetism works in both natural and engineered systems. A lot of appliances in the electrical grid operate on AC, but robotics operate on DC. In fact, DC is very compatible with solar and renewable energy, meaning you may not even need a converter or inverter when dealing with renewable energy in robotics. Copper wiring acts as the medium to carry the electrical current, transmitting energy from the inverter to where it's needed. An inverter is an electronic device that converts direct current, DC, into alternating current, AC. The DC to AC conversion is essential because the output from sources like solar panels or batteries is DC, but most household appliances in the electrical grid require AC. It's interesting to note that many robots use DC, which differs from the typical AC used in most appliances. DC is preferred in robots for several reasons. DC motors are simpler to control than AC motors and allow for straightforward speed and torque control, which is crucial for precise movements. Many robotic systems are powered by batteries, which inherently provide DC, making it more efficient to use DC for the whole system. Additionally, DC components are often smaller and lighter than their AC counterparts, a significant advantage in robotics where space and weight are limited. DC power devices tend to be cheaper because they are lighter and use fewer materials. Fewer components mean lower costs, and simpler designs reduce the complexity, making DC systems more efficient and cost-effective. DC motors also produce less vibration than AC motors, reducing wear and tear, which leads to lower maintenance costs and a longer lifespan. In terms of renewable energy, solar panels convert energy to DC, and since robotics use DC, this is a natural pairing. However, not all renewable energy sources produce DC. When we talk about direct current, it's a steady flow of electrical charge in one direction, while alternating current reverses direction periodically. DC is used in devices requiring steady, consistent power, like robotics and battery-powered devices. AC, on the other hand, reverses direction and changes polarity. This reversal between positive and negative voltages creates a wave-like flow, where the current moves in one direction during one half of the cycle and reverses during the other half. Rectifiers convert AC to DC. A half-wave rectifier allows only one half of the alternating current waveform to pass, creating a pulsed DC output. This pulsed output is essential for pulse width modulation (PWM) systems, where the voltage fluctuates between 0 and the peak value of the AC signal during the positive half cycle. The positive half cycle refers to the portion of the waveform where the voltage is above 0. In summary, DC systems are lighter, cheaper, and more efficient for many applications, especially in robotics and renewable energy systems. Converting between AC and DC is essential in integrating these systems with the broader electrical grid. Converting AC to DC involves turning alternating current into direct current. The point of an inverter with built-in rectification is to convert AC to DC, which is essential because many electronic devices require DC to operate. A half-wave rectifier allows only one half of the alternating current waveform to pass through, creating a pulsed DC output. This occurs because only one half of the AC waveform is able to pass through, resulting in a pulse. This is where pulse width modulation, (PWM), comes in. A half-wave rectifier effectively blocks the other half of the AC waveform, which creates a pulsed output. During the positive half cycle, the voltage fluctuates between 0 and the peak value of the AC signal, producing a series of pulses. The positive half cycle refers to the portion of the alternating current waveform where the voltage is above 0. When looking at a number line, you have 0 in the middle, the positive side on the right, and the negative on the left. The positive half cycle is the part where the voltage is above 0, which creates the pulse in the alternating current waveform. Examining the phase of a sinusoidal waveform using geometrical representation, particularly in Cartesian coordinates, is very helpful for visualizing and understanding its properties. In a Cartesian coordinate system, the x-axis, which is the horizontal line, divides the plane into 4 quadrants: 1, 2, 3, and 4. On the right side of the x-axis, it's positive. We're working on an infinite line where 0 is in the middle. You go upwards on the y-axis, and that's positive. Below 0 on the y-axis is negative. So you have 2 infinite lines, going in infinite directions, and we're only looking at this two-dimensionally. On the right of the x-axis, the positive side, is where the 0, or the center of the Cartesian coordinate system, is located. On the left side, it's negative. So, to be clear, in a Cartesian coordinate system, the x-axis typically represents time, while the y-axis represents the voltage or current of the waveform. When we look back, we are essentially measuring the amplitude, which is the maximum value of the waveform. That maximum value indicates the strength of the signal. When we talk about the strength of sinusoidal waveforms, or the system's signal, we're often looking at examples like linear power supplies, half waves, and full waves. Geometrically, when we think about these waveforms using the Cartesian coordinate system, we also consider dimensions and electromagnetic fields. The question then becomes, how do these elements come together? How does that relate to calculus? Are we using calculus to measure these things, and what would they look like geometrically on a Cartesian coordinate system? Okay, and again, we're going to think geometrically. So we're just going to use the axiom of an infinite line. Even though the waveform is a lot more complex than this, we're going to keep it simple. We'll use a line with infinite directions. You have 0 in the middle, positive on the right, and negative on the left. A half cycle means half is on one side, on the positive side, because it's higher than 0. So, in a typical sinusoidal AC signal. Wait, let's stop there. What is a sinusoidal AC signal? What even is sinusoidal? A sinusoidal AC signal refers to an alternating current signal that varies in a smooth, continuous wave pattern, described mathematically by a sine function. We know the sine function. A sinusoidal waveform is characterized by *its smooth, periodic oscillation, and the shape of the wave resembles the sine function, which is mathematically defined as y t equals a asterisk sin 2 pi ft plus phi, etc. So, you have the frequency, which tells you how many cycles occur in 1 second, measured in Hertz Hc, and that's the variable f. Then we have t, which is time, and the phase shift, which determines the wave's starting point. The characteristics include the maximum value of the waveform, indicating the strength of the signal. Then, there's the frequency, which determines how quickly the waveform repeats. For example, 60 Hz means the waveform completes 60 cycles in 1 second. The period is the duration of one complete cycle of the wave, and it's the inverse of frequency. So again, the inverse of frequency meaning how many cycles the waveform completes in 1 second. That's the frequency. The inverse of the frequency is the period, which is the duration of one complete cycle of the wave. So, one complete cycle means 60 periods if we're talking about 60 Hz. When we're looking at a period, we're looking at, for example, in 60 Hz, we have 60 periods. The phase indicates where the wave starts in its cycle, which can affect how multiple signals interact. So, it's helpful to look at the phase of the sinusoidal waveform in a geometrical way. This is where you get into Cartesian coordinates. The strength of a sinusoidal signal is often measured by its amplitude, which represents the maximum voltage or current level of the waveform. In a Cartesian coordinate system, this is the peak value on the y-axis. When examining types of power supplies, we can look at linear power supplies and rectifiers. Linear power supplies provide a steady output voltage, typically using transformers and linear regulation. Their output may be smoother, but is less efficient compared to switched-mode power supplies. Rectifiers, which we've been discussing, include half-wave and full-wave types. These devices convert AC to DC. Half-wave rectifiers only allow one half of the alternating current wave to pass, resulting in a pulse output. In contrast, full-wave rectifiers utilize both halves of the waveform, yielding a smoother direct current output. In Cartesian coordinates, a sinusoidal waveform is represented as a smooth sine curve oscillating above and below the x-axis, where the x-axis represents time. The curve consists of one half above the x-axis, positive, and one half below, negative. Thus, a half-wave rectifier is always positive, while a full-wave rectifier produces both positive and negative outputs, effectively creating two waves. Geometrically, a full-wave rectified sine wave combines both halves of the alternating current signal, resulting in a continuous waveform oscillating above the x-axis. If you visualize both halves of the sine wave, you can see oscillations that relate to circular motion. By considering the sine and cosine functions as projections of a point moving around a unit circle, the x-coordinate represents the cosine, horizontal position, and the y-coordinate represents the sine, vertical position. This movement creates a sine wave when plotted onto the x and y-axis. In essence, we are plotting the path that electrons take in an alternating current system, where they oscillate back and forth in response to the alternating voltage. In an alternating current, AC, system, electrons oscillate back and forth in response to alternating voltage. This means that while the voltage is changing, the electrons are also moving in reaction to that change. Voltage represents electrical potential difference. It's a measure of the potential energy per unit charge and indicates how much energy electrons can gain or lose as they move through a circuit. When you look at the sine wave of a half-wave rectifier, it appears above the x-axis, indicating a positive voltage. The peak of the wave represents the maximum electrical potential or voltage of the alternating current. The sine wave shows a continuous oscillation of voltage over time, typically plotted with time on the x-axis and voltage on the y-axis. The highest point of the curve represents the maximum positive voltage, while the lowest point, or troughs, represent the maximum negative voltage. Troughs occur when the wave dips below the x-axis, indicating negative voltage values. During these troughs, the current flows in the opposite direction compared to when the voltage is positive. A half-wave rectifier allows only the positive half of the sine wave to pass through, effectively blocking the negative portions. This is the main function of rectifiers. They convert AC to DC by blocking the negative charge. As a result, the rectifier allows only one direction of current to flow, maintaining a positive output. In a half-wave rectifier, the negative cycles of the waveform are blocked, meaning that during the negative phase, no negative voltage appears in the output. Instead, the output consists solely of positive half cycles, creating a series of positive voltage pulses. This transformation results in a unidirectional flow of current, characteristic of direct current, DC. We get into pulse width modulation, PWM. The term itself suggests a modulation happening with the width of the pulse. So, let's break that down. PWM is a technique used to control the amount of power delivered to a load by varying the width of the pulses in a signal while keeping the frequency constant. This means you're controlling the power, but it's important to clarify that when we say controlling power, we're not directly manipulating the frequency or phase of the sine wave. In PWM, you're primarily controlling the average power delivered to a load by adjusting the width of the pulse rather than changing the sine wave itself. This can be confusing, as power can mean different things, such as voltage. That's why it's crucial to understand the vocabulary and the concepts behind these terms, which can deepen your understanding. PWM modulates the duty cycle of the signal. The duty cycle refers to how long the signal stays active compared to how long it is inactive. In computing, for example, PWM controls the amount of power delivered to the load, and the longer the active state, the more energy is delivered. PWM modulates the duty cycle of a switch, usually a transistor, adjusting the ratio of the time the voltage is on compared to when it's off. With PWM, you're not adjusting the voltage directly. Rather, you control how much of that voltage can pass through the gate to reach an inactive state. In this context, a transistor acts as an electronic switch, allowing current to flow when the PWM signal is high and stopping it when the signal is low. Thus, when you're controlling voltage with PWM, you're effectively determining how much of the supply voltage reaches the load. By rapidly switching the transistor on and off, the average voltage experienced by the load can be adjusted. For example, a 50% duty cycle means the load receives power half the time, resulting in a lower average voltage. The inactive state refers to when the transistor is off and no current flows, which corresponds to zero voltage on the y-axis of a graph. During the on state, the PWM signal shows pulses above the x-axis, and the width of these pulses determines the average power delivered to the load. When visualizing alternating current and PWM in a Cartesian coordinate graph, the alternating current waveform typically appears as a sine wave, oscillating between positive and negative values. In contrast, the PWM signal appears as a series of rectangular pulses characterized by their width, duty cycle, and frequency. The duty cycle, expressed as a percentage, represents the width of the rectangle in the PWM graph. A wider rectangle means a higher duty cycle and thus more average power delivered to the load, while a narrower rectangle indicates a lower duty cycle and less power. The length of the rectangle represents the time during each pulse, contributing to the total duration of one complete cycle, which includes both the on and off times. If the PWM frequency is constant, the total time for one cycle remains the same, but the pulse width can vary to adjust the power output. In summary, on a Cartesian graph, The x-axis represents time, while the y-axis represents voltage. Each PWM cycle appears as a rectangular pulse above the x-axis during the on state, followed by a drop to zero during the off state. As you move along the x-axis in the positive direction, you encounter successive rectangles that indicate when the signal is on and off, signifying positive voltage applied to the load. This complexity is why I find it takes a long time to absorb information, as I often spend an hour discussing and reflecting on just one paragraph of text. Now we get into pulse width modulation, PWM. If you look at the vocabulary, there's a modulation happening with the width of the pulse. Let's break that down. PWM is a technique used to control the amount of power delivered to a load by varying the width of the pulses in a signal while keeping the frequency constant. Essentially, you're controlling the amount of power, but we need to clarify what controlling the amount of power means. Are you controlling the frequency of the sine waves? When we talk about hertz, are we managing the frequency, phase, and periods? In PWM, you're primarily controlling the average power delivered to a load by adjusting the width of the pulse, rather than directly manipulating the frequency or phase of the sine wave itself. This can be confusing, which is why it's important to define these terms clearly. Power can refer to many things, including voltage, so visual aids and geometry are essential for understanding these concepts better. PWM modulates the duty cycle of the signal, which refers to the alternation between inactive and active voltage states. In our example, we're using computing terminology because of my background. PWM controls the amount of power delivered to the load. The longer the active state, the more energy is delivered. PWM adjusts the duty cycle of the switch, usually a transistor, which changes the ratio of the on-time voltage to the off-time voltage, 0. Essentially, PWM modulates the duty cycle, determining how much of that on-time voltage is allowed to reach a specific point. So again, we're examining it in a way where there's a sort of break, an on and off state, not technically on and off, but there's a bridge, a gate that could be represented by a transistor. We're not adjusting the voltage itself. Rather, we're controlling how much of that voltage can pass through the gate to reach an inactive state, which is 0 on the x-axis, time, and also 0 on the y-axis, potential. In PWM applications, a transistor acts as an electronic switch, allowing you to control the flow of current based on the PWM signal. When the PWM signal is high on, the transistor permits current to pass through. When the signal is low, off, the transistor stops the current flow. When controlling voltage, you're not directly changing the voltage itself or the maximum electrical potential. The PWM signal determines how much of the supply voltage can reach the load. By rapidly switching the transistor on and off, you can adjust the average voltage that the load experiences. For example, a 50% duty cycle means the load receives power half the time, resulting in a lower average voltage. The inactive state in our example refers to when the transistor is off and no current flows, corresponding to the 0 level on the y-axis, voltage. When the transistor is on, the PWM signal shows pulses above the x-axis, time, and falls back to 0 during the off state. The width of these pulses, the time spent above 0, determines the average power delivered to the load. When comparing alternating currents and pulse width modulation, you can visualize them on a Cartesian coordinate graph. The alternating current waveform is typically plotted as a sine wave, oscillating between positive and negative values, creating a smooth, continuous curve. In contrast, the PWM signal appears as a series of rectangular pulses characterized by their width, duty cycle, and frequency. The alternating current and PWM can be represented as distinct waveforms on the same graph. The height of the pulse remains constant, representing the supply voltage, while the width varies depending on the duty cycle. The duty cycle, the width of the rectangle on the graph, determines the average power delivered to the load. A wider rectangle means a higher duty cycle, resulting in more average power, while a narrower rectangle means a lower duty cycle and less power. The length of the rectangle can represent the time during each pulse, which is the same as the period of the PWM signal. The total duration of one complete cycle includes both the on and off times. If the pulse width modulation, PWM, frequency is constant, the total time for one cycle will remain the same, but the pulse width can vary to adjust power output. On a Cartesian graph, the x-axis represents time, while the y-axis represents voltage. Each PWM cycle appears as a rectangular pulse above the x-axis for the duration of the on state, followed by a drop to zero during the off state. The length of the rectangle represents time, as we're looking at the x-axis, which is time. Moving in a certain direction, the length of the rectangle corresponds to the time, since we are progressing infinitely in the positive direction. On the Cartesian coordinate graph, as you move positively along the x-axis, you effectively track the progression of the PWM signal over time. The length of the rectangle in the PWM signal indicates how long the voltage remains at its maximum during the on state, and this length is measured along the x-axis. As you move from left to right on the x-axis, you encounter successive rectangles that show when the signal is on and off. When the rectangle is above the x-axis, it signifies that a positive voltage is applied to the load, allowing it to receive power. Once the rectangle ends and the signal drops to zero, it indicates the off state during which no power is delivered. There are variances and nuances to consider, but this is a good summary of the concept. It takes me a long time to read books because I'll read one paragraph and spend an hour discussing all the insights to fully absorb it.